So, we talked about what quadratic equations are. We understood they are an equation in degree 2 with variable which are of the form ax squared plus bx plus c is 0. We also understood what we mean by roots, which are done for all type of equation, the solutions for a particular quadratic equation. Now, a very important and interesting part of quadratic equation is to understand the nature of roots from one part of the formula. But before that, a very important exercise would be to just recapture what we know about what we have learned in all these years about the type of numbers. We need to refresh our ideas of the number system. So, over the years, as man has been understanding more about numbers, different new revelations came which made us understand there are so many different types of numbers. So starting from how a small child would possibly classify numbers, we'll just go through this exercise in a short but as effective a way as possible. So we start with natural numbers. Now these typical names that have been given were on the basis of what the initial understanding of the type of numbers is. Now first thing that is there is we have natural numbers. Natural numbers are also called counting numbers like 1, 2, 3, 4, 5 and so on and so forth. All of them are positive numbers and they are wholesome numbers. They are not based on 1.5, 2.5. They are all whole natural numbers. So all these are the common counting numbers, the way man started counting number of days or the number of trees and all. So at that time the concept of zero was possibly not introduced. So we have the natural numbers as a normal counting numbers. Now after the zero was introduced, 0 plus the set of natural numbers, that is 0, 1, 2, 3, 4, 5, 6 and so on and so forth would form the set of natural numbers. In other words, whole numbers is the same as natural numbers along with 0. So it's just one number more than the set of natural numbers. Now again, these are of course whole counting numbers. Then people understood the concept that numbers could also be negative. Like for example, any kind of removal of something, reduction of something is a negative process. So somebody is losing money. So we say minus 4, minus 5. So thus the understanding of negative whole numbers started. So the integers include all these numbers like minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on and so forth. So that means, it's in simple words, it means all the negative whole numbers plus all the positive natural numbers along with 0. In short, if you see, the set of natural numbers is a subset of whole numbers and whole numbers is a subset of the set of integers. So among these three, this is the biggest group of numbers. This one is a part of this one is a part of this. So in short, natural, whole and integers means real whole numbers without 0.75, 0.6, but they may also include negative numbers when you're talking about integers. So this is something we all know. Then a rational number. In simple words, rational meant a sensible number which has a rational existence. So generally a rational number could be any fraction of the form say p by q, where p and q are integers and q is not 0. So it could be say 3 by 4, where 3 and 4 are integers, and say 5 itself, 5 can be written as 5 by 1, or minus 7 can be written as minus 14 by 2. This is also a rational number. Or 22 by 7. Now when we come to 22 by 7 in the next section, we will understand something very interesting about 22 by 7. 22 by 7, 5 by 18, all these are rational numbers. So in other words, if you have even minus 6 can be written as minus 6 by 1. So even minus 6 is a rational number actually. So in other words, the set of rational number includes all integers plus non-integral fractions. So the fractions could be more than 1 or could be less than 1. So in other words, among these four, among the set of natural numbers, whole numbers, integers, rational number, Rational number contains all the previous ones. So a rational number is any integer can be expressed as a rational number because you just have to put it as something, some integer upon another integer. Say 4, you can write it as 8 by 2, so it becomes a rational number. So these are all common ones which we say. Now, very interesting thing about rational numbers is when you try to actually convert them to decimal form. Say 3 by 4 is actually 0.75. So when you convert it to decimal form, it terminates. If you take 10 by 3, you write it as 3.33333. So this one, you never get a remainder 0, but this particular remainder 3 keeps on repeating itself. So you get 3.33333. So it's a recurring form. So in simple words, if you look at a rational number, any rational number, say minus 6 by 1 is minus 6.0. So whenever you convert a rational number to a decimal form, either it would terminate, as in this case, say this can be written as minus 6.0, or the decimal form would be recurring. It would be either recurring or terminating. Then you call that as a rational number. So these are all common numbers which we are familiar with. Now an irrational number could be something like this: cube root of 2, fifth root of 7, square root of 3. So all these are irrational numbers. Even pi is in kind of an irrational number, or to be understanding, but actually deeper form, pi is called what is called as a transcendental number. But for our understanding, we can take pi as an irrational number. Now you have to understand one thing. There is pi, there is 22 by 7. We often take pi as 22 by 7, which doesn't mean that pi is equal to 27. Pi is not equal to 22 by 7. 22 by 7 is the most approximate value of pi. Pi is an irrational number which is defined as a ratio of the circumference of a circle to its diameter. Pi d upon d is pi. But we often take the value as 22 by 7 because it is the nearest approximation. So 22 by 7 is rational, but the actual value pi is irrational, because if you try to convert it, say root 3 you do by division method, you will get 1.732, so on and so forth, which will neither terminate nor recur. So the decimal representation of an irrational number will be neither terminating nor recurring. It will just go on and no remainder would repeat itself. And one more very important thing about irrational number is that all these rational numbers belong to one set. Natural, whole number, integer and rational fall in one set. But irrational can never be rational. Rational can never be irrational. In simple words, no number can be rational as well as irrational. We'll do a diagrammatic understanding in terms of sets as to how it goes about. So this is the basic understanding. So quickly, natural numbers are simple counting numbers, whole numbers are simple counting numbers along with 0. Integers are counting numbers plus 0 plus the negative whole numbers. A rational number could be fractions, it could be whole numbers, it could be integers. So all fractions where the numerator and denominator are integers with the denominator not 0, right? All these will form the set of rational numbers, and rational numbers, if you convert them to the decimal form, they will either terminate, that is, you'll get the remainder as 0 sometime, or the remainder would recur at regular intervals. So the decimal representation is either terminating or recurring. Irrational number is totally different from all these. It could be square root of any prime number, cube root of a number which is not a perfect cube. If you take fifth root of 32, it may deceptively look like it is a irrational number, but it's not so, because fifth root of 32 is 2. So it is not an irrational number. So irrational number is represented by q dash. So it is not an irrational number. A rational number is represented by capital Q. So Q and Q dash means they are totally different sets. They are complements of each other. There is nothing common between them. No number can be rational as well as irrational. So these are the common type of numbers. We need to understand the nature of the numbers, because a very important aspect of quadratic equation is what is the nature of roots. It is with the help of the nature of roots that we need to understand whether it is necessary to solve a quadratic equation further, whether it is admissible, whether it would be right to solve a quadratic equation or no. For that, we need to understand the nature of roots. Now, from this, we have irrational number. We move a little beyond that, and we have the set of real numbers. Now, the real numbers that are there are everything. Rational numbers, that is q plus q dash put together will form the set of real numbers. So real number is a combination of all rational numbers and irrational numbers together. They are of course two sets which are totally disjoint. They don't have anything common, but if you sum up the set of real numbers and non-real numbers, that is irrational numbers, rational and irrational numbers put together, this plus this is given the set of real numbers. And then we have what are called as imaginary numbers, and it's almost like you can see the words if you look at from the English point of view, real and imaginary. Imaginary means non-real numbers. These are all numbers which do not exist in our common understanding. Say for example, somebody asks you to find a number which one multiplied by itself gives -5. But we know that whenever you multiply two numbers, 2 into 2 is 4, -2 into -2 is also 4. So the square, when you square a number, you can never get a negative answer. So if you're getting a negative answer, then it is not a real answer, because the moment you multiply a number by itself, it cannot remain negative. It would be either 0, say 0 into 0 is 0, -3 into -3 is 9, 3 into 3 is also 9. So on squaring, a number can never remain negative even if the number is originally negative. So, but an imaginary number could be something like this, root -5. Now this is a little, if you look at it from the set of view of real numbers, root of -5 is something which we cannot relate to. So this is actually equal to root 5 into root -1, which is the same as telling root 5i. The root -1 is called I. So root 5i is an imaginary number, because such a number does not exist in the set of real numbers, because the moment you square a number, it becomes negative. Hence, equivalently, square root of a negative number does not exist in the set of real numbers. So if you come across such a number, we call such a number as an imaginary number. It's purely imaginary. But suppose you have complex number. A complex number is a combination of a real number A and an imaginary number bi. So for example, 5 plus root of -2, which will be the same as 5 plus root 2i. That is, you are adding a non-real number, an imaginary number and a real number, then you get a complex number. In simple words, every imaginary number is a complex number, because root 5i can be written as 0 plus root 5i. So it's a combination of a real part and a non-real part. But every complex number is not a imaginary number, because an imaginary number does not have a real part in it. So a complex number is a combination of a real part and an imaginary part. So we have to understand that whenever in quadratic equation we get this kind of situation, what to do with such a things. So these are the kind of numbers. So if you just quickly recapture whatever are the type of numbers. So you have the set of whole numbers here, natural numbers. Then you have the set of whole numbers. Then you have the set of integers. Then you have the set of rational numbers q. So in simple words, natural number is part of whole number is part of integer is part of irrational numbers, of rational numbers. And outside this, here this side, you have the set of irrational numbers, that is q dash. And this two put together will form the set of real numbers, q and q dash put together. And beyond that, here you have the complex numbers. Here you have the complex numbers. And within complex number, you have the set of imaginary numbers. That means imaginary number you have, and you have the set of complex numbers. So an imaginary number is a complex number, but there are many numbers which are complex but not imaginary. So hence this is the way we can roughly understand the basic set of numbers. There is of course one more set of numbers which are also called transcendental numbers, but that is very fine division. Transcendental numbers are also special type of irrational numbers. Among them we said pi and also e, which is also an irrational number whose approximate value is around 2.7128 and so on and so forth, with no recurrence happening. But we need have to bother about that. We have to understand what rational number means, what irrational number means, and when will it trigger when you have an irrational number. Whenever you get a square root, a non-real number, whenever you get a square root of a negative number, or when you square a number you get negative answer, then it cannot be a real number, it is an imaginary number. So this is the general summation of the type of numbers. Now, of course, the best learning will happen when we actually apply these, right? Now, how do we understand these concepts of numbers, and why do we need to understand them with respect to quadratic equations? Simple answer, as I mentioned earlier, we need to understand them to get clear about our idea of nature of roots, and from the nature of roots, how we can define the solutions of a particular quadratic equations. So from here, let's move over to the nature of roots.